First up, I just want to very quickly explain what the Newton-Raphson method is doing, and then we'll talk about actually applying the iterative formula that we have to use. So let's imagine I've got some sort of function that looks like that, and we want to find this point here, the root. What we do is we pick a point on the graph, and then essentially the method draws a tangent that goes down. Now, where that hits the axis, we then find the value of y that would go with that, and we repeat. And you can sort of see, using this iterative method, we get closer and closer to the solution, as close as you want, in fact. Now, the formula you can derive using this approach is given by this. So this first question, we basically need, it's a sort of a substitution question. For us, we're trying to solve f of x equals 0. So f of x is equal to x cubed minus x squared minus 5x plus 10. And then we need the derivative, this f dash x. So that is going to be 3x squared minus 2x minus 5. And therefore we substitute these in. Xn plus 1 for us is going to equal xn minus f of xn. So that's just this thing I had before, but with a little xn in there, because these are now this is now a specific x value, but it's going to be it's going to change as n changes. All over f dash n, so that's going to be 3xn squared minus 2xn minus 5. All right, now the question's asked me to write it in a very specific form. You can see the denominator looks good. I just need to tinker with it very slightly. I want to put it over a common denominator, so I'm going to need to actually write the xn as it's going to be, I'm going to need to times that by 3xn squared minus 2xn minus 5, and then divide by it as well. That is to get the common denominator. Okay, and then I've got the rest of it as well, so I'll put that back in a second. So now if I can, it's going to be 3xn cubed minus 2xn squared minus 5xn. And then I'm minusing all that stuff at the top here. Okay, and then expand the bracket. I think it's enough to just sort of go straight to the answer. So 2xn cubed, and this is going to become a minus minus. It's going to become minus xn squared. I've got a plus 5xn, so that's actually going to cancel. So I'm just going to be left with minus 10. Just quickly compare it. Do we get that? 2 minus 1 minus 10. The xn term is not there, which makes sense. And we know at that point we've done it correctly. So part B asks us to apply this iterative formula with an initial value of x1 equals minus 3, and then find x2, x3, and x4 correct to 4 significant figures. Oops. All right, so this is how you can do it really effectively. Hopefully you've learned this already, but we don't just stick it in like 4 times. What we do is we use the answer button. So I'm going to do minus 3 equals, and then that is stored in my answer button. So now I can do 2 answer to the power 3. Okay, just basically replace my xm by answer. At the moment, I'm putting in -3. So let's see what we get. So I get -73/28. Right, more importantly, I get -2.607. I could, write it down and then round it. I'm just going to go straight for it though. Like this, you're basically going to be marked on whether you've rounded it correctly. That will be expected at this point. So yeah, and then if I press equals again, I'll be putting my new value in. So -2.535. And we're actually following these steps that I said. Look, you can see, like we started sort of at minus, I mean, it's not quite right, is it? But -3, and then we're sort of got here, we're getting closer and closer to the roots. Okay, the sketch isn't accurate, but you got the idea. And then, so the last one, I just need to do it again. And it just changes very slightly, -2.533. And those are the values that they wanted. All right, on to part C. So we've got, and this is quite good, like the fact it's now saying use a change of sign method to show that alpha, that's the root, equals -2.533 is correct to four significant figures. The fact that we got that for our fourth iteration is pretty promising for that solution. Okay, so how do we show that it's correct to four significant figures? Right, well, think about a number line, and here we've got -2.533. The next one, if we're going positive, would be -2.53 2 going that way because it's less negative. And here -2.534. So how do I show that it would be correct to 2.533 to four decimal places? I want to find a sign change between the midpoints. Essentially, the upper and lower bound if you are rounding something to four significant figures. So that's going to mean we're going to look at -2.533 and -2.535. And if we can show that one of them is, say, negative and one of them is positive, then it must be that in between it's gone through, because we've got a sign change, it must have gone through the axes. And because I'm looking between these limits, it's going to definitely round to -2.533 to four significant figures. So that is sufficient. Therefore, I need to actually return to my original function. Or actually, let me grab it from here. So f of -2.535 first up. I'm just going to have to put that in my calculator, I think. I suppose I could use the answer button. That might make life a bit easier. Then I don't have to write it out lots of times. So -2.5335 equals, and then it's going to be answer cubed. I get -0.0127. So I've just shown that it's negative here. There's not much I can do at this point, but do the same again. You could, in theory, use the table function. I don't know. I think this is probably just as quick. Just be careful. Okay, we're expecting this one to be positive, and it is. 6.612 times 10 to the -3. So very small, but positive. Less than 0, greater than 0. So what this means is because f of x is continuous, there is a sign change. F of x is continuous. I think it's good to say that because, for example, with 1 over x, you get a sign change. 1 over x looks like this. You get a sign change, but there's never any root because there's a discontinuity. But if it's continuous, then what it means is that we don't exactly know how, but somehow it's gone through the axis and then got to there. So there's a sign change. F of x is continuous. So there is a root between minus 2 point. I'm probably writing more than I need to here. And that is enough. Therefore, alpha equals minus 2.533 to 4 significant figures. Right, the last part, explain why the Newton-Raphson method with initial value x1 equals minus 1 would not converge to alpha. So let's put it in. x1 equals minus 1. x2, well, something's going to happen when we put it in. So x2 would actually be minus 2 minus 1 minus 10. There's nothing wrong with that. Divided by 3, because minus 1 squared is 1, plus 2 minus 5. And here's the thing. This is going to become minus 13 over 0. So that's not defined. I know I'm writing all over the place a little bit. I'm just trying to have the question at hand. So not defined. x2 cannot be found. So the method will not converge. Sorry, it's a bit messy. Converge to alpha. And if you want to know why, like, I mean, lots of numerical methods have flaws. You know, they might not always converge. And the reason this one won't converge is that there is some sort of, there's a turning point. So maybe it looks like that, in fact, because it is a cubic. And if you put in a value here and you try to draw a tangent, well, guess what? You're never going to meet the axis. And that's exactly what's happened here. So when you use a starting value that gives you a gradient of 0, of course, if you look at the Newton-Raphson formula, you're dividing by 0 and you're going to get into problems. And that is what's happened here. Nice.